Hello everybody. Today we will be looking at the USACO 2021 December Contest Silver Problem 2, Connecting Two Barns. So Farmer John has a farm, farm consisting of n sets of n fields, right? Conveniently numbered between 1 and n. Between each of these fields are m bidirected paths, each connecting a pair of fields. Now there are two barns. The first one is on field 1, and then the second one's on field 1. N. Farmer John would like to ensure that there is a way to walk from field 1 to field N. And in order to do this, he is willing to build up to 2 new paths to accomplish this goal. Due to the way the paths are fields are situated, the cost of building a new path between fields I and j is just I minus j squared. So we have to help Farmer John determine the minimum cost needed, such that the barns 1 and n become reachable from each other. So let's look at the solution. So we are going to be using connected components in binary search. So our main observation in this problem is that if we break the graph into all of its connected components, right, we observe that the final graph with a path between node 1 and node n will always look like this. So we'll have one component, and then we'll connect it to a middle component, and then we'll connect it to the component with n. Or we'll just have the component with 1 directly connected to the component with n. And here is how that would look. So say we have this graph and n is equal to 10. So in order to only build two paths, the only way we can connect this one to this one using these two is just if we were to connect like 3 to 4, for instance, and then we'd connect 5 to 8, or 3 to 6, and then and then 7 to 8. So it's always going to be the first barn connected to a barn in the middle connected to the barn with n. So here are our steps in solving the problem, right? First of all, we want to find all of the connected components using DFS and just store them as an array. And then we want to sort them all, and then we want to loop through each of the components, and then we use binary search to find the two closest components between so say in our loop we are looking at this component. So we would want to use binary search to find the two closest nodes in these two components, right? And we will say, so we'd find that the two closest nodes are 3 and 4, and we'd say that we would draw a path from 3 to 4, and then we'd also use binary search to find the two closest nodes between these two, between this one and the last connected component. And what we would do is then we would find the two closest, and we'd see, okay, it's 5 and 8, and then we draw a path from those two, and then we just calculate the cost of drawing these paths, and then we would essentially just store that and see if that is the minimum. And then we also want to calculate the cost between directly connecting the component with 1 to the component with n. So let's look at the code for this. So first of all, we want to set the recursion limit because we're going to use a DFS to find the connected components, and obviously we don't want to get wrong answers because recursion limit is too low. So we're just going to do a very basic DFS. So we're just going to go ahead and take in visited and component, which is an array that contains all of the current nodes the current connected component we're looking at. So what we're going to do then is we're just going to set the visited of our node to true. We're going to add it to our current components, and then we're just going to run the DFS on all of its neighbors. Now, when we get all the connecting components, we'll have a big visited array, and then we'll have a components array. And then essentially for each node that is not visited, we will run the DFS, and we will say that that node is the start of a new component. And then after we run the DFS, we'll add that component to our components array. So like, say we wanted to look at this one, we would do the DFS, we'd look at this, and we'd see that our big component just has 1, 2, and 3, and then because this is not connected to any other node, we could not go on, continuing our search. So we would have to essentially just go to the next unvisited node, which would be 4, and then we do our search, and we find next the node in this component is 5, and then we store that in our components array. And then again, we could not do any more searches because it's not connected to anything else. And then we do for 6, and so on and so forth. So then we have our binary search function, which essentially finds the closest value in a certain array R given a certain target. So this is a pretty basic binary search. All we do is we just go through the array, and then we just change our bounds if our current mid value is equal to target, less than target, or greater than target. Well, if it's equal to the target, we return the mid, because we know that if we see that, that means that the mid value is actually in the array. Now, all we do then is we just do some checks, and we either want to return array sub low or array sub high, and essentially if the differences between array sub low and in target and array sub high in target, if this one is less than this one, then we return array sub low, because we know that array sub low is closer to target than array sub high. Otherwise, we return array sub high. Now, in our find two closest element functions, all we do is we take two arrays in, and then we just store which one is smaller and which one is larger. Then we have a min difference variable, which is what we're going to return. And then for each element in the smaller array, we will essentially just set the min difference to the minimum between itself and the difference between x, which is the element we're looking at in smaller, and finding the closest value of larger, and 2x in larger. So essentially, for each value, we will find the closest value to that value in our other array, and what we will do is, in our other array, we will find, so we will then store that as our answer. And essentially, if we do that, we loop through every single value, find the closest value to that value. We are guaranteed to find the two closest values and have that as our difference. And then we just go ahead and return the minimum difference. So now, when we actually process each test case, because each input does not have only one test case, it has multiple test cases, because there are t subtest cases. What we do is we extract n and m, which is the amount of nodes and the amount of edges. And then for each edge, we just go ahead, or of course we first have to make the graph, and then for each edge, we just go ahead and draw a path from the two nodes to each other. Then we go ahead and get all of the connected components of our graph, and then for each of the connected components, we sort them, like said in this. Now, if there's a connected component with 1 and n in it, we just print 0. Because say, okay, let me just erase all of this stuff. Say n was 3. If this were to be our only array and n was 3, then we would not need to draw any paths, because n and 1 are in the same connected component. So thus, there has to be, because they're the same connected component, there has to be a way to go from 1 to n. So thus the answer is 0, because we would not need to draw any new paths. Otherwise, if we don't find a component like that, we will essentially just go ahead and have a few variables. So we'll have our answer, and then our component with barn 1 in it, our component with barn n in it, and all of our other components. So then we'll go through all of our components. If there is barn 1 in the component, then we'll set our barn 1 component equal to the current component. Otherwise, if there is barn n in the component, we will set our barn n component equal to our current components. And then finally, otherwise, we'll just add it to the array of other components that don't contain barn 1 or barn n. Now, for every component and other components, we essentially treat the current component we're looking at as the middle component. So if we're looking at this component, we'll go ahead and draw a connection and draw a connection. And the way we calculate the cost between that is we essentially find the two closest elements between the barn 1 component and the current component, and then we square that because I plus I minus j squared, and then we find the minimum, the closest two elements between the barn end components and the current component. And you can see this find two closest elements returns a difference. So, and the difference, and it's said in the problem that the cost is I minus j, or the difference. And then we just set the answer to the minimum of the current answer and then that quantity. And finally, we want to check our current answer because it might be optimal to draw a direct pathway from barn 1 to barn n. So we will find the closest two elements and then we'll square that, and that will be our final cost because there's no middle component. And then we will set the answer to the minimum of that and this. And then we print out answer. That's a 107 line long marathon. We could like eliminate pretty much this whole function instead and just use bisect with a few lines, but manual binary search is very cool and I like manual binary search, so I'm going to keep this function in. And yeah, so now let's go ahead and submit it to the grading servers to see if our code works. And you can see we pass, give it a sec because we're using Python, but we pass all of the test cases. Thank you very much for watching.